Hello and welcome to a digital lecture for Salt Lake Community College. This lecture will be the second to cover section 4.2 for Intro to Statistics, considering one sample means with a t-distribution. This video will discuss a concept known as the central limit theorem heavily, discussed in the first lesson video for section 4.2, so please review that once more before continuing with this video. To begin, we have a concept known as the degrees of freedom, which is a parameter for the t-distribution, denoted as df, which describes the precise form of the distribution. The degrees of freedom describes the shape of the t-distribution and are related to the sample size using the formula of n minus 1. The larger the degrees of freedom, the more closely the distribution approximates the normal model. If you want to think about why the formula for the degrees of freedom is what it is, n minus 1, I recommend thinking about it like this. When calculating any statistics, you need at least one observation in order to do anything, like calculate an average. However, all other observations past that initial one help to determine how much a value varies away from the initial observation. And so the calculation of n minus 1 is showing the number of observations in the dataset that vary and are free to do so to help calculate some statistics. To determine how the degrees of freedom affect the distribution we'll be working with, we have what is known as a t-table available in the appendix of your textbook, which is used in place of the normal probability table when the population standard deviation sigma is unknown. As a summary of the t-distribution from this video and the prior one, use the t-distribution for inference of the sample mean when data comes from a random sample or randomized experiment, observations are independent, and approximately normal. That last note of it being approximately normal, note that observations can be considered approximately normal as long as there isn't extreme skewness or outliers. This was known as the central limit theorem. You may relax the approximately normal condition even further as the sample size increases. For example, the data distribution may be skewed when the sample size is at least 30. This tends to be our benchmark for the central limit theorem. Before applying the t-distribution for inference about a single mean, we have three conditions, and these are the same three conditions discussed previously, although more in depth. We have first that data comes from a random sample or randomized experiment. Data are collected appropriately if they come from observational units that are randomly selected or randomly assigned to treatments. Secondly, we have independence of observations. We collect a simple random sample from less than 5% of the population, or the observations are independent. And lastly, we have, again, observations come from approximately normal distribution. We often, one, take a look at a plot of the data for obvious departures from the normal model, usually in the form of prominent outliers. And two, we consider whether any previous experiences alert us that the data may not be approximately normal. However, since the t-distribution is robust, we can relax this condition. Moderate skew is acceptable, and strong skew is acceptable when the sample size is 30 or more. On the next page, we will see a red dotted curve that represents the standard normal z distribution, and the blue solid curve that represents a t-distribution with maybe 10 degrees of freedom. What we're going to do here is add and label what a t-distribution would look like if it instead had 5 degrees of freedom and 20 degrees of freedom. What I will first do is draw a green curve that represents a t-distribution with 5 degrees of freedom. Recall that the lower the degrees of freedom, the less we assume that it will approximate the normal curve, which again is represented with the red dots. So, if we have a lower degrees of freedom, what we tend to expect are thicker tails and a distribution that may seem normal but is a little bit more flattened out. Maybe something that looks a little bit more like this. However, if we increase that to a larger degrees of freedom, maybe 20 degrees of freedom, we'd expect the distribution to look even closer to the normal distribution than it already does. We note that the blue curve for 10 degrees of freedom is pretty close to the normal distribution, but with thicker tails on both the left and the right. So when we increase to a 20 degrees of freedom, it should get closer to a normal curve, closer to the red dots. So it may be something that looks kind of like that. A curve that is somewhere in between the blue curve and the red dotted curve. If you have any further questions, be sure to review the example videos or ask your instructor.